So now we're going to talk about the rational root theorem. First, we're going to recall a few things. An integer is a number that is either a counting number, which is 1, 2, 3, 4, however high you want to count up, 0, or the negative of a counting number. So that is the set of the integers. Remember this from at the very beginning of the semester. A rational number is a number that can be written as a fraction with an integer as the numerator and an integer as the denominator. So anything that is a fraction like 1/2 or 3/4, that's a rational number. A number like 0.1 is a rational number because you can write that as 1 over 10. However, numbers like pi, the square root of 2, square root of 3, those are not rational numbers because you cannot write those as fractions of integers. Then you remember from our Introduction to Polynomial Functions video, this is the form of a polynomial function, standard form. The lead coefficient is the coefficient of the term that has the highest exponent. So this a sub n is a lead coefficient. And the constant term is the number that doesn't get multiplied by any x. It's that last little constant. And finally, a root of a polynomial is the same as a 0. And a number is a root of a polynomial if you can plug it into that function and get 0. You will also want to remember the factor theorem from the last video. But now let's have the rational root theorem. If k is a rational root, that is a number that is a rational number, that is a root of the polynomial function, and that polynomial function has integer coefficients, then k is equal to p over q, where p evenly divides the constant term and q evenly divides the lead coefficient. So let's look at an example. So here is a polynomial function with integer coefficients. Each one of these coefficients is an integer. It has 5 roots, and here are those 5 roots. At first glance, it might look like there's only 4 things in the set, but this plus or minus the square root of 2 means that we're including both the positive square root of 2 and negative of the square root of 2. Then the number 2/5, 4, and negative 7/3. Now, not all of these are rational roots. The square root of 2 is an irrational number, so it does not need to fit into this rule, because this starts out with if k is a rational root. So we will look at the other 3 roots. 2/5 is clearly a rational number. It's a fraction with an integer on top and an integer on bottom. And notice that, so k is p over q. P, the top, has to evenly divide the constant term. So let's look. 2 evenly divides negative 112. That's true. That's an even number, so 2 evenly divides that. And 5 evenly divides 15, which is also clearly true. Now let's look at 4. It might not be obvious that 4 is a rational number because it doesn't look like a fraction, but remember you can write that as 4 over 1, so it is rational. When I consider it over here, k is equal to 4 over 1, where 4 divides the constant term. That's true. You could punch that into a calculator to make absolutely certain, but 4 does evenly divide 112. And 1 is our denominator, evenly divides the lead coefficient. And of course, 1 evenly divides any integer, so that's fine. And finally, negative 7/3 is a rational number. Negative 7 does evenly divide negative 112. You can test that with a calculator if you don't believe me. And 3 does evenly divide 15. So that is the rational root theorem. Now that might just seem like a random, bit of trivia, except it is useful for finding all possible rational roots. So let's look at this. If k is a rational root, I'm not sure why I'm reading that over. I'm just repeating our rule up here. That's from the rational root theorem. We can use this fact to generate a list of all possible rational roots. For example, I have got this function, 4x cubed minus 13x squared minus 50x plus 75. So I want to take the factors of the constant term because I'm going to want numbers that evenly divide the constant term. So that's going to be the factors of 75, which will be 1, 3, 5, 15, 25, and 75. Let's see. Yes, those are the factors of the constant term. Those are all of the numbers that evenly divide 75. We're also going to want to know the factors of the lead coefficient. So the numbers that evenly divide 4 are going to be 1, 2, and 4. Notice right now I haven't been all that worried about whether things are positive or negative. I'm just listing out positive factors of each of these numbers. But when I consider anything that can be written as P over Q, where P evenly divides 75 and Q evenly divides 4. Negative numbers can meet that qualification, so I will want to have a plus or minus of everything that I consider. And so all of my possible rational roots are going to be every combination of numbers from this set over numbers from this set, which is a very long list for this particular problem. So I've got plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. Notice how I'm taking everything from this set and putting it over everything from this set. You could also, you don't need to write 1 over 1 unless you want to for emphasis. Here I really wanted to emphasize that we are doing 1 over 1, and that is 1. But those are all the possible rational roots. Now this is a cubic function. It has at most 3 roots. So it is definitely not true that all of these are actually roots. But if this cubic function has rational roots, they must be in this list. These are not all actually roots. But we could test using synthetic division to see whether these are roots or not. We'll have a video that does that in a moment. Let's do another example first. So let's find all possible rational roots of f of x equals 4x cubed minus 17x squared plus 18x plus 8. So we'll factor the constant term. 8 is my constant term. The factors of that are 1, 2, 4, and 8. Those are all the numbers that will evenly divide 8. My factors of my lead coefficient. This is actually the same as the previous problem, 1, 2, and 4. And now I'm going to want every possible combination of factors of my constant term over my factors of my lead coefficient. So I've again got plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4, plus or minus 2 over 1, etc., etc., etc. Now here, a lot of these can be reduced, so let's go ahead and reduce every fraction that we can. So I've got 1, 1/2, 1/4. This is just a 2. That's another way of writing 1. That's another way of writing 1/2. So notice that I do have some repetition in this list. And since repetition is always ignored in sets and order doesn't matter in sets, I can write this as a nicer looking list. This is absolutely true that all of my possible rational roots are in this set, but I can write that set as just plus or minus 1/4, plus or minus 1/2, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. These are the possible rational roots of this function. And again, they're not all actually roots. There are 12 things in this set. It might look at first glance like there's 6, but remember each plus or minus means that this represents 2 separate numbers. And in order to find out whether something is actually a root, you would need to either plug it in and see if you get a 0, or perform a synthetic division. The synthetic division is going to be more useful because then we'll have a quotient and then we can factor that, and that will allow us to find all possible roots, which is what we're going to do in the next video. So now watch the video on finding all roots of a polynomial function.